Hello everyone. Um, so now we have completed chapter 8, chapter 9, and chapter 10, which deals with this confidence interviews and hypothesis test. Okay, so today in this video we will start with the simple linear regression. So the linear regression is one of in fact, the most important topic in statistics. So up to now, what we do is we just try to make preparation for the simple linear regression. So up to now, most of the things that we did was in fact the preparation for simple linear regression. Of course, the things that you have learned so far, the hypothesis testing, the confidence intervals, and so on and so forth, well, they can be used in many applications like simulation or in statistical quality control or in even machine learning. But the linear regression is one of the most important topics for especially industrial engineers in routine daily life, in work. So before getting into the linear regression, so we just give some definitions and then some examples on this. And after after that, we will give the definition. Okay? So simple linear regression, which is SLR, we just abbreviated with SLR. This is a statistical method that allows us to summarize and study the relationships between two continuous, especially quantitative variables, X and Y. Okay? So there are several names used for X and Y. So X is the predictor or explanatory, or most of the time we will use this, the independent variable. Okay. Y, on the other hand, Y is the response or outcome or the dependent variable. So what does it mean, dependent or independent? Why do we mean by being dependent or independent? Well, so this means that the value of y, okay, depends on x. So x is independent, it just changes, I don't know, randomly or under control with under the control of the experimentalist or the scientist. And the value of y changes with x. So it depends on the what? The value of x. Okay. So, well, we have in fact two types of relationships. Okay? The first one is the deterministic. Well, the equation exactly describes the relationship between two variables. Okay, so just look at this. So, for example, if you just measure the temperature of the air, well, then if you know the Celsius, you can just convert it to Fahrenheit by just multiplying it with 1.8 and adding 32 over that. Okay? So this is a deterministic relationship. Okay? It's for sure. Or the circumference of a circle is equal to pi times the diameter of that circle. Okay? So again, that's for sure. Or the volts of the volt on a wire is equal to the current times the resistance of that wire. But in statistics, of course, we're interested in statistical relationships. Okay? What does it mean? Well, the relationship between variables is not perfect. Okay. So, for example, let's look at this one. So the response variable or the independent variable is y. Okay, it's the weight. So that's something that I'm just using in my courses most of the time. This is a good example, I guess. And the predictor variable is the height. Okay. So your weight just depends on your height. Okay? So what you expect to see is if your height just gets taller and taller, if somebody is taller, then what you expect to see is that, well, it's or his or her weight is high. Okay, so there is a relationship between the weight and the height. So for example, let's look at these 10 many students, okay? So 163, 164, these are the height of the students, and these are the corresponding weight, okay? Well, so let's look at this one. So I just plot them, okay? So this is the guy who has 163, okay? And how about this? I don't know, but this is something 59, I guess. Let's see. That's 58. So this is 58, okay? And this guy is 164. Okay, just look at this. And this is what? This is 55. Okay, this is 55, right? And so on and so forth. So this is the first guy, this is the second guy, third guy. What I do is I just plot them, right? So as you see, well, as the weight goes up, okay, the height goes up as well. So there's a relationship between them. That's for sure. The weight, the weight increases with the height, but it's not a deterministic relationship. Okay. So there's a positive linear relationship between them, but the relationship is not perfect. So in fact, the plot exhibits some trends. Okay, well, it just goes up, and there's some scatter. Okay, there's a scatter in the data. So therefore, this is what we call a statistical relationship. Okay, that's not a deterministic. So another example is that, well, the size of a shop, okay, and the annual sales. Okay, so what we expect to see is as the size of a shop, as the size of a market just goes up, then the annual sales goes up. Okay, so this is what you expect. But this is not a deterministic relationship. You cannot say sales is equal to 37.5 plus 2.3 times the size of the shop. You cannot say this, right? So what you expect to see is as the size of the shop just goes up, okay, then the sales goes up as well. So you will expect to see something like this, okay? So you might think of this at your home. So what can be some examples for this, okay? So, well, just come here. Well, so as you see, there is a trend in the data. And now I just give you two lines which summarizes or which gives the relationship between the weight and the height. So the first line and the second line. Okay. So the first line is the orange one, this one. Okay, this is line one, and this is line two. Okay. So line one, well, it says the weight is equal to minus 470.2 plus 3.2 times height. And line 2 says minus 384 plus 2 plus 2.7 times height. So both of them just summarizes or tries to give the trend in the data. So it just gives the relationship between height and the weight. And the question is, well, which line is better? Okay, which line is better? Okay, which line is better? Okay. So let's think a little bit. How can we say that this line or this line is better? So for example, if you have another line, something like this, you will probably say that, well, this line is not a good one. Or if you have something like this, okay, probably you will say that, well, that's not a good one. So how to say that whether this blue line or orange line is better than the other, okay? How can we say this? How can we quantify this? Okay, so in order to say that which line is better, let's introduce some common notation. Okay, so yi denotes the observed response for experimental unit R. So what is yi? Let me just go back to the data. So this is your yi. Okay, so this is y1, right? This is y1, the weight. So it's the 163 here, and this is 58, right? This is the first data. So y. So this is y1. Okay, this is the weight of the first observation, and this is x1. This is x2, this is y2, this is y3, this is x3, and so on and so forth. Okay. That's great. Then, okay, if I did not predictor variable, that's okay as well. Okay, this is fine. This is fine. And y I had is the predicted response for experimental unit I. So what does this mean? Well, y I had, so just go back. Let's see this one. So this is the uh, this is the formula for line 1. So what does this formula say? Let's concentrate on this a little. So this formula says that, well, this is a line formula, right? So this is a line formula. What does this mean? If you just give a height here, if you just provide a value here, 3.2 times height minus 470.2, it will just give you a height, okay? So for example, if your height is, let's say, 100 times 3.2, okay, that's not a good idea. So let's say if your height is, for example, if your height is, let's try to find, so remember, x1 was equal to 163 centimeters, okay? So what I would try to do is, I would just put it into the formula, minus 470.2 plus 3.2 times the height. I've just put it here to find the value. Which value? Um, let me just give me a second. So this is 3.2 times 163 plus, not a plus, minus 470.2. So that's equal to 51.4. So what is this? This is simply just, this is what? This is 163. And this line 1 is the orange line. If you just move direct to up, okay, move directly to up, and this is where it just hits the line. This is 51.4. Okay, this is 51.4. What is this? This is the value, okay, predicted for the for the first let's say student, for the first student by the first line, okay, by the first line, which is the orange line. So what is this? This is in fact y1 hat. Okay, so this is the predicted response of the predicted response for the first student by the first line. Okay, so let me just go back and see what is the second guy. The second guy is 164. The third guy is 166. Let's see them. 164. Okay, so 164. Let's put 164 and calculate it. So I have my calculator in front of me. Okay, so 164. That's equal to 54.6. Okay, so let me just write it where. So if x2 is equal to 164, then y2 hat is equal to 54.6. If it is 166, then x3 is equal to 166, then we will see that y3 hat is equal to 61 kilograms. Okay? So what are these? These are the predictions made by the first line. So this is the prediction for the second student. This is the prediction for the third student. Okay, so this is 164. If you just follow this, right? If you just follow this to here, okay, so this is what? This is 54.6. And for 166, let me just move it like this. And this is equal to what? This is equal to 61 kilograms. Okay. So these are the yi hat. So two different lines have different yi hats. Okay. So the equation for the fitting line is equal to yi hat is equal to b0 plus b1 xi. So for the first line, you have minus 470. So you have minus 470.2 plus 3.2 xi, right? This is equal to yi hat, right? So this is my first line. Okay. So in fact, this is what we did, right? 51.4. This is the prediction, and so on and so forth. So we just talked about this. Of course, so this is 51.4. This is my prediction. This is the prediction of the first student. Well, how about its real weight? The real weight is equal to 58. What is my prediction? Y1 hat. That's equal to 51.4. As you see, all predictions almost have errors, right? So what is the error here? Well, 58 minus 51.4, that's equal to 6.6 kilograms. This is my error, okay? So I just predicted, or this line has just predicted the weight of the student with an error of 6.6 kilograms. So the error can be defined as the yi, the real value, okay, the real value minus the predicted value. Okay, this is what we call an error, EI. So, well, in fact, EI are the vertical deviations, right? So remember in our example, so let's say if this is 163, okay, then the corresponding value is 51.4, and this is the real value of this guy, which is equal to 58, right? And what we do is we just find the error, which is 58 minus 51.4, and this is, in fact, this distance, right? The distance between this point and this point, right? Okay, so distance is 6.6 in our example, which is equal to E1. So this is equal to E2, this is E3, this is E4, this is E5, right? And it just goes like this. Okay. So a line that fits the data better will be the one for which n prediction errors, okay? The n prediction errors, that is the error for each of your data point, are as small as possible in some overall sense, okay? So what I will try to do is, I will just try to minimize these errors. And this is how we just, so for this, we have what we call a sum of the squared prediction errors, or sum of squared errors. So the sum of squared errors is equal to, so this is I from 1 to n. So this is equal to just sum the squared of all of the errors from 1 to n. Okay, so this is what we call an SSE, right? SSE. Okay. So why do we take the square? Remember, when we are talking about the variance, there are some pluses and minuses. In order to eliminate them, we just take the square. Okay. So just look at our example. So this is yi, right? This is yi hat. So this is yi hat, sorry. So this is yi hat. EI and EI squared. Look at this. This is EI. So this is the real value. This is the predicted value. This is the error. This is the square of that error. And after that, you just sum all of them. It turns out that this is the sum here is that 141. The sum here is 126.27. Okay. So the error here is smaller, right? This is smaller SSE. Okay. Smaller SSE. Hence, you can say that well, the second line is better. Okay. Now the question is, what is the best line? So I have two lines here. I can say that, well, this line is better, but the question is, what is the best line? So the best line can be found so that, well, so this is the function, this is the error that you have. You can find, okay, so just look at this one. Yi is given, so this is, so SSE is equal to sum of EI squared. EI is yi minus yi hat. Instead of yi hat, I can just write b0 minus b1 xi, okay? So this is given, this is the data, yi's are given, xi's are given, these are the data as well. What I'm trying to find is b0 and b1, okay? So if you calculate b0 and b1, it means that, well, you find the line, okay? So just find B0, B1 so that it minimizes the SSE. Okay. So in fact, this is a function of what? This is a function of B0 and B1. So what we will try to do is just minimize this function. Okay, just minimize this function. How to minimize a function? Uh, hmm, So what we will do is we will just differentiate the SSE with respect to B0 and B1 and then set the partial derivative is equal to 0. Okay, so this is what we call a method of least squares. So if you just take the derivative with respect to B0 and B1, okay, this is what we have. And at last, okay, I will just skip them. So at last, the formula for B1 is given like this. This is the formula for B1. Let's see this. It says that, well, just take the difference between the ith x and its average and multiply it by the ith observation of yi minus the average of y, okay? Sum this up to n, and divide it by xi minus x bar squared, which is summed from 1 to n. Okay, so this is B1. How about B0? After you find B1, what you do is you just write the average of y minus B1 times the average of x bar. And this is how we get B0. Okay. So for our example, if you just try to find B0 and B1, it turns out that, well, the best fit is this. So this is my B0, this is my B1. Okay. So just look at here, right? So this is X bar, right? This is X bar, right? So this is Y bar. This is sum of xi squared. This is xi times yi, right? So why do we need them? Okay, just look at here. Well, so this formula is good to represent it. This formula is good to represent B1, but this formula is good when you just calculate it. Okay, so this is good for making calculations. Okay, good for calculations. Okay. And this is good for definition. Good for the definition. Okay. So what is the meaning of B0 and B1 here? So B0 is the height of, so if you just put 0 here, what does it mean? That's the height of a person that's the, so if you just put 0 here, then you will find the weight kilogram of a person whose height is 0. In fact, for this particular case, it doesn't mean anything. Okay? So you don't have any person whose height is 0. Okay. How about B1? How about B1? So B1, just look at here. So B1 is the change in the value of the weight, in the value of kilogram, then you just increase the height by 1 unit. Okay. So for example, the difference between the height of a guy who is 180 and the weight of a guy who is 181, that's equal to 2.7661 kilograms. So what does this mean? This shows the change in the weight of a guy per 1 centimeter. Right? So this is a clear meaning, a very important meaning, and it just shows the sensitivity between the response variable or the dependent variable and the independent variable. Well, this is the result for this regression in Microsoft Excel, but we will do several examples in R. Okay? So we will see all of them in detail, but if you just look at here, well, the coefficients here, well, this is what? This is B0, okay, this is B0, and this is B1, okay, this is minus 396, this is 2.76, okay. So what does this mean? This means that, well, your regression is equal to Y is equal to minus 396.3 plus 2.766112 times what? Times x. Okay. And what is this? As I said, we will in detail analyze this table, but this one just gives you the SSE, okay? So remember, in the previous example, one of them was around 140, the other one is 125, but it turns out that the minimum SSE is given by this line, and the value of SSE is 113.34 and 54.